Section 1. A Symphony in a Sphere. Unpacking the aerial shell. Every time a firework screams into the night sky, it feels like a violation of the quiet darkness, a beautiful and sudden intrusion of light and sound. We crane our necks, mouths slightly agape, awaiting the inevitable boom. The splash of color follows. It is a moment of communal awe, a shared gasp at a spectacle that feels both magical and chaotic. But behind that fleeting burst of glory is a meticulously crafted object, a small, dense package of controlled violence. This object, known as an aerial shell, is the heart of any professional fireworks display. It is less a random explosion and more a precisely engineered device, designed to perform a single spectacular task high above our heads. An aerial shell is essentially a sphere or cylinder made of thick, glued paper or plastic. Inside this casing, everything has its place, arranged with the care of a watchmaker. The most important components are the stars. Stars are the tiny compacted pellets that will ultimately produce the brilliant points of light we see. Each star is a carefully concocted chemical pill, a dense nugget containing everything needed to create a specific color. Tucked alongside these stars are other crucial elements: lift charge, time fuse, stars, burst charge. The engine of the firework is black powder, a simple but potent mixture of charcoal sulfur. At the very bottom of the shell, a portion of it is designated as the lift charge. When ignited, this charge burns with incredible speed, producing a massive volume of hot gas that propels the shell out of its launch tube, a piece of equipment called a mortar, with tremendous force. Deeper within the shell's core lies the burst charge, another pocket of black powder. Its job is to detonate at the flight's apex, shattering the casing and flinging the stars outward in a predetermined pattern. Connecting these explosive elements is a network of fuses, the unsung heroes that dictate the fireworks' rhythm. A primary fast-acting fuse is lit on the ground, which in turn ignites the lift charge. Simultaneously, this initial spark also lights a separate, slow-burning time fuse that snakes its way up into the shell's interior. This time fuse is the firework's internal clock. As the shell hurtles upward through the air, this fuse is steadily burning its way toward the central burst charge. The length of this fuse is calculated with extreme precision, ensuring the shell reaches the perfect altitude before the final, sky-painting explosion is triggered, turning potential energy into a dazzling display of kinetic art. The life of a firework is dramatic, violent, breathtakingly short, beginning with a single spark in the dark. A pyrotechnician follows a carefully scripted plan, sends an electrical signal, or uses a direct flame to light the main fuse. The aerial shell sits snug inside its mortar tube. This initial ignition is nearly instantaneous. The first component to react is the lift charge, that powerful pocket of black powder at the very bottom of the shell. It combusts with ferocious energy, converting solid chemicals into a massive, expanding cloud of hot gas in a fraction of a second. This explosive expansion of gas needs somewhere to go, and the only path is up. Pressure builds inside the mortar tube like a cannon launching the shell skyward at speeds that can exceed 300 miles per hour. As the shell is violently ejected, the force of the launch simultaneously ignites the time fuse. This fuse is a critical element, a slow, steady burn designed to act as a countdown timer during the shell's ascent. It smolders quietly, hidden from view as the shell climbs higher and higher, arcing gracefully against the black canvas of the night sky. The shell's upward trajectory is a battle against gravity and air resistance. It loses speed with every foot it climbs, eventually reaching its highest point, or apogee. This is the moment the entire launch was designed to achieve. Just as the shell seems to hang motionless for a split second, the slow-burning time fuse finally reaches the central burst charge nestled among the stars, triggering a second, much more contained explosion. This internal detonation ruptures the shell's paper casing and ignites the stars packed inside. The burst charge explodes with enough force to hurl the now burning stars outward in all directions. The careful placement of these stars within the shell determines the firework's final shape. If the stars are arranged evenly around the burst charge in a spherical pattern, they create a classic round peony. If arranged similarly, they can form a chrysanthemum. If packed into a heart-shaped mold, the resulting pattern in the sky will mirror that design. If arranged in concentric circles, the resulting pattern in the sky will mirror that design. Each star, now a flying ember, burns brightly for a few seconds, tracing a brilliant path as it falls back to Earth, creating the magnificent fleeting patterns that we all know and love. Section 3. From Bamboo Cracks to Royal Spectacles, a Fiery History. The story of fireworks does not begin with a sophisticated chemistry lab, but with a simple piece of bamboo tossed into a fire. Over 2,000 years ago in ancient China, people observed that green bamboo stalks, when heated, would trap steam and air inside their sealed segments. The mounting pressure would eventually cause the bamboo to burst with a loud, sharp crack. This startling noise was believed to have the power to ward off evil spirits and bring good fortune. These primitive firecrackers, known as baozhu, the true revolution came much later, around the 9th century, when Chinese alchemists stumbled upon a far more powerful noisemaker. While attempting to create an elixir for immortality, they mixed together sulfur, charcoal, saltpeter. The result was not eternal life, but a volatile black powder that burned with astonishing speed. Gunpowder. It didn't take long for inventive minds to realize the potential of this new discovery. They began packing the powder into paper tubes and bamboo stalks, creating the first true firecrackers. These were used to add a much louder and more impressive bang to festivals, weddings, military celebrations. News of this explosive black powder, along with other exotic goods, eventually traveled westward from China along the vast network of trade routes known as the Silk Road. By the 13th century, the recipe for gunpowder had reached the Middle East, where Arab scholars studied its properties and called the saltpeter component Chinese snow. From there, it spread into Europe, where it was initially adopted for military use in cannons and early firearms. However, its festive potential was not overlooked. Italian pyrotechnicians, in particular, became masters of the craft, developing elaborate aerial shells and turning fireworks displays into a grand form of public entertainment for religious festivals, royal events. Fireworks soon became a symbol of power and celebration throughout the European courts. When colonists traveled to the New World, they brought this tradition with them. In early America, fireworks were a part of major public gatherings. On the very first anniversary of the Declaration of Independence in 1777, the celebrations in Philadelphia included a grand display of fireworks. Founding Father John Adams had even predicted that the occasion would be celebrated by future generations with illuminations from one end of this continent to the other. For centuries, the pyrotechnic palette was surprisingly limited. Early fireworks glowed with the simple, fiery colors of any burning material. Faint oranges, soft yellows, bright whites, the brilliant saturated colors that define modern fireworks displays were impossible to create. That all changed in the 1830s, when Italian chemists discovered the secret to painting the sky. They realized that adding specific metal salts to the pyrotechnic mixture would produce intensely colored flames. The underlying principle is a basic concept of chemistry. When certain metals are heated to extreme temperatures, their atoms emit light of a very specific color, a unique spectral fingerprint for each element. The intense heat generated by a bursting firework star energizes the metal atoms within the salt. This energy pushes their electrons into a higher, unstable orbit. As the electrons inevitably fall back to their normal stable state, they release the extra energy in the form of a particle of light, a photon. The color of that light is directly related to the amount of energy released, which is a fixed characteristic of each specific metal. This is the same scientific principle demonstrated in high school chemistry labs, where students dip a wire coated in different chemicals into a Bunsen burner flame to see it change color. Creating these brilliant colors requires a precise recipe for each star. A beautiful, vibrant red, for example, is most often created using strontium salts. For a deep, rich blue, historically the most difficult color to produce, pyrotechnicians rely on copper salts. A bright, vivid green is achieved with the addition of barium salts. Other metals contribute to the dazzling array as well. Calcium salts produce a distinct orange hue, while sodium, the same element that makes table salt, burns with an intense yellow. Bright, glittering whites and silvers are not produced by salts, but by burning actual metal powders like magnesium or aluminum at incredibly high temperatures. Magnesium aluminum. To make these colors pop with the necessary brilliance, the metal salt can't work alone. Each star's chemical recipe includes 3 key ingredients working in concert. First is the oxidizer, a chemical that releases oxygen to allow the mixture to burn rapidly and intensely, even in the low oxygen environment high in the atmosphere. Next is the fuel, which provides the substance that burns to generate the immense heat needed to excite the metal salts. Finally, many color recipes include a chlorine donor. This special ingredient helps the metal atoms release their light more efficiently, resulting in deeper, more vibrant and stable colors, especially for challenging blues and greens. The creation of a single firework is a remarkable fusion of disciplines. It is a work of craft demanding the hands-on skill of a carpenter, demanding the hands-on skill of a baker. Pyrotechnicians must carefully mix precise chemical recipes, ensuring that each ingredient is measured correctly for both performance and safety. They then pack these stars, the burst charge the fuses into the paper shell, arranging them in patterns that are part art and part geometry. This hands-on process is a tradition passed down through generations, blending old-world craftsmanship with modern precision. At the same time, every firework is a self-contained chemistry experiment launched into the sky. The principles of thermodynamics govern its powerful ascent, while the science of atomic emission dictates the colors of its bloom. The careful selection of metal salts like strontium for red, barium for green, is a direct application of quantum physics, manipulating the behavior of electrons to paint with light. The precise ratios of fuel oxidizer chlorine donors are a delicate balancing act of reaction kinetics, designed to maximize brightness and color purity while controlling the burn rate. A firework is a fleeting, explosive demonstration of fundamental scientific laws. This journey, from the ancient discovery of cracking bamboo in China to the intricate chemical formulations of today, charts a human fascination with light and sound. The history of fireworks is a history of our own growing understanding of the physical world, a quest to control fire and transform it into a source of celebration rather than destruction. What began as a way to scare spirits evolved into a tool for royal pageantry and is now a universal language of joy, marking holidays and milestones across cultures. Each explosion is a nod to those early Chinese alchemists, Italian masters